this is perfect timing for our next talk. So our next talk will be from Weaviate. And our next talk was, I originally wrote this intro for Philip, but we're actually going to have another person from Weaviate. We'll have Zain Hasan. And Weaviate is doing some incredibly innovative work in the generative AI space, in the space of vector databases. So earlier we heard from Frank, who's from Zillis, who also works on a vector database. And now we'll hear from Zain. And from what I hear, Zain is an expert on this generative feedback loop and is an expert on building very robust retrieval augmented generation applications. And so, since Zain is already here, I'm going to welcome Zain to the stage, and I'm going to take myself off of the stage.
Thanks. Thank you so much. So last minute replacement for Philip here, but I'll try to fill the big shoes here. So I'm going to talk a little bit about advanced retrieval augmented generation techniques and show you how you can do that with Weaviate. So like was mentioned already, I work for Weaviate. My background is in engineering, and then in graduate school I went into data science. I've been in the machine learning field for about 9 years now. The most important thing to know about me is that I'm very passionate about AI and the good that it can do for us. Right? Okay, so on to the topic. RAG is a very kind of nebulous, it sounds a lot more difficult than it is term. So I'm just going to ground my talk in this one example. So think about an average human doctor, and we're going to try to build a RAG pipeline that emulates or assists a human doctor. And so the average human doctor, at least in North America, studies for 7+ years after undergrad. So the total study period is about 11 years that they go through. And in their entire lifetime as a doctor, they see about 100,000 patients. And so when you walk into the doctor's clinic next, they're kind of they're going over everything that they've learned, all the patients that they've seen, and they're trying to understand which of those experiences are relevant to your use case and which ones are irrelevant. Right? So if we're going to build a chatbot that emulates what a human doctor does, it's going to need to be pretty advanced. Right? It's going to need access to a wide knowledge base, similar to a knowledge base that a real doctor has. So 11 years worth of study, 100,000 patients worth of experience. And honestly, the knowledge base can even be larger. It's going to need to efficiently search over that knowledge base to find out which historical patients are relevant, which publications and which information from medical literature is relevant to the patient that's right in front of them. It's going to need to reason or understand the information that it's searched over and what applies and what doesn't apply to the current patient. It's going to need to be explainable, and this is particularly important in the medical domain. And you could take this application, you could kind of strip out the medical component and add in whatever your component is, but at least for medicine, it needs to be explainable. The doctor needs to prescribe the right thing to you for the right reasons. And so the AI needs to give you the right answer for the right reasons as well. And we need to explain that as well. And to complete the circle here, it needs to be real time. So it needs to be performant, and it needs to do this pretty quickly. So if this is the example that we're going to ground the rest of the talk in, let's move forward with this. Right? At Weaviate is an open source vector database. We love everything open source. So every slide in this talk is going to use an open source tool, and the link at the bottom is going to take you to that resource. So whether it's a machine learning model, whether it's on Hugging Face, whether it's a GitHub repo, everything is linked at the bottom. So you can literally rebuild this entire talk and the tool that I'm talking about here yourself if you wanted to. And it's all open source with permissive licenses. All right, awesome. So the approach that I'm going to talk about here is something that I've named the RAG Doctor. And how it works is we're going to take the simplest approach of how people use language models. So a patient walks into your clinic, they tell you they have so-and-so problem. The simplest thing you can do is just provide that over to a language model, and the language model then outputs some form of cheat sheet that the doctor can then read and use. Right? And this doesn't have any RAG. So we're going to add some components to this. Right? we're going to add some form of knowledge base. So this is information about past patients, information from medical literature, and we're going to store that into a database. So I've got here a vector database, but technically this can be any database. It doesn't need to be a vector database. And before we go to the language model, we're going to take a kind of a tangent. We're going to take a detour, and we're going to take the patient information here, and we're going to use that to query the vector database. And the vector database then outputs relevant responses from this knowledge base, right? So this might be millions of articles. It extracts out the 5 articles that are relevant to this patient, and now we can augment that. We can stuff that into the prompt that was going to the language model. Right? And so this is our basic RAG approach. And the rest of this talk is going to be elaborating how you can go above and beyond. How do I improve on top of this? Right? So in this case, we've got our indexing phase, and I'm breaking it down into 3 phases because I'm going to propose at least two mechanisms to improve each phase. Right? So we've got the ingestion and the indexing phase. How do you get your data and put it into the vector database? We've got our retrieval phase. How does the vector database retrieve relevant articles that are pertinent to that particular patient? And then we've got the generation phase. This is where the language model takes that patient's information and everything that you've suggested that might be relevant and then formulates some form of answer. And so this is our basic RAG stack. We've got the retrieval piece, the generation piece, and then we've got the glue that sticks those, integrates those together. Okay, so in our particular example, the data set is all important, right? It forms the knowledge base that we're going to RAG over. In this case, this is an open source data set called the PMC patients data set. And this is a live data set, by the way. They keep adding to it and they keep increasing the amount of data in here. When I built this application, it had about 170,000 patient summaries. So one patient summary is the account of one patient walking into the clinic, things that they were prescribed, tests that they had run. So you've got 170,000 of those, more than any patient, more than any doctor has seen in their in their working time in the profession. And then it also has about 1.4 million articles from PubMed. So these are abstracts, and there's also embeddings for all of these that are generated beforehand that you can just start using and insert into a database. The images, sorry, the data can also be images and charts, but for the purpose of this example, we're only going to think of it as text. Right? So these are just texts that are going to be embedded using text models. But later on, you can also try to see how you can pass in images and charts for these. And because the data set is a retrieval benchmark data set, we know the ground truths. So given any patient, the data set tells you which 5 patients are the closest. So you can use this to benchmark your vector database as well to see how well your retriever is working based on the ground truths that this data set gives you. So in this data set, you've got kind of relevant article ground truths as well as relevant patient ground truths, right? So the relevant articles come from here and the patient ground truths come from the 170,000 patient summaries. So that's going to formulate our knowledge base. And this knowledge base is honestly larger than any doctor has available when you walk into the clinic. Okay. And then the vector database we're going to use here is Weaviate. And we've talked about this. Previous speakers have mentioned this. So I'm going to quickly gloss over this. But the main idea here is a vector database allows you to scale vector search up to billions of documents, right? So here we've got about 1.6 million objects. If we had billions of objects, we would still be able to perform in real time and scale this chatbot up. And it performs semantic search. It performs search using machine learning models that embed data, and this is a topic that's already been covered. And so the idea here is the patient tells you that they're having pain in their left shoulder and they have numbness in their thumb and index finger, and that goes into your vector space, and out comes retrieved objects. And so here I'm showing an example of multi-vector retrieval where I can retrieve from an index of patient cases. These 3 patients here that I've got might be the most relevant to answer this query. And I might also retrieve from an index of articles on the other hand, right? So now I can kind of reason over both patient cases as well as articles. So Weaviate supports multi-vector retrieval as well. Okay, so now for the rest of the talk, I'm going to try to go into the details of how we can do better. Right? Based on this basic RAG stack, what are some improvements that we can add to the indexing, the retrieval, and the generation phase that'll take us above and beyond the basic RAG stack. And so the point here is not for everybody to become an expert in RAG. Uh, the point is to introduce these techniques to you and to link relevant resources so that after these 30 minutes, you can have jumping off points where if you want to do query transformation, query rewriting, you want to do re-ranking, hybrid search, some of the techniques that I'm going to talk about, you'll have resources that will allow you to introduce those into your pipeline and evaluate those as well. Okay, so let's start. Let's start with these so-called advanced RAG techniques. So we're going to start off at the bottom, and better RAG starts off even before you've indexed your data into a vector database. Some of the choices you have to make are how do you chunk your data? And so typically, the reason why this is a difficult choice here is because depending on your domain, depending on what your data is about, you want to extract out text that is semantically coherent, right? You want to have kind of one trail of thought in one chunk so that the vector that you generate is captures that information. If you've got too big of a chunk, then you might have multiple semantic meanings behind that, and then the vector is not able to represent the vector that gets generated to capture that chunk can't follow along, right? And if the chunk is too small, then it might not have any meaning at all, right? So imagine if my chunk is just one word or one token, then in that case, it has no contextual meaning. Right? I can't understand a lot from that. So there's a whole separate blog on this about choosing chunks that are too large or too small and why this is not a trivial kind of hyperparameter to set. Right? So typically what people do is called fixed size chunking. And so this is from Greg at Data Indie, where you can give it your entire document and you can say, I want chunk sizes of 35 characters or 300 characters. And the important thing here is the chunk overlap, right? This is important because you don't want context to be left off right at the ending point or the starting point of the next chunk. So you want there to be a little bit of overlap so that if two chunks that are consecutive are retrieved, you have some information before and after what's happening. So this is basically the starting point of how people get introduced to chunking. I'm going to talk about two more options that you can use when you're chunking. Right? One option is called semantic chunking, and this is a relatively simple idea. The idea here is that you can go sentence by sentence, and your job is to identify how similar the previous sentence is to the next sentence. If they're similar enough, you don't create a new chunk. You just append the second sentence to the chunk of the first sentence. And every incremental sentence, you decide whether that sentence is different enough from the previous sentences that are already in the chunk to to kind of to, uh, justify its own chunk, or whether it should just be accumulated into the previously growing chunk. And so this is called semantic chunking because you're trying to understand the meaning of the previous sentence. And you do that by embedding the previous sentence, and you embed the second sentence. And then you calculate the cosine distance between them to get an idea of how similar or dissimilar those two sentences are. So when you do this, so this is a graph that's a bit involved, so I'll talk about what you're looking at here. On the x-axis, you've got the sentence index, right? So you might have the 257th sentence, you might have the 7th sentence here. And notice how the chunks are not a fixed size anymore. They're based on the semantics. So the idea here is this is a Paul Graham essay. And it, as if you read top to bottom, as long as the topic that he's talking about doesn't change, it'll belong in the same chunk. The minute he changes topics, it'll create a new chunk because the semantics change, and now you chunk it right there. So every peak here is one where you're going to chunk, and everywhere the semantics, the cosine distance is lower than that threshold peak, you're going to accumulate in the same chunk, right? So this might be a kind of a quick divergent tangent where he's talking about a topic and then he diverts over to a topic for a couple of sentences. It deserves its own chunk, and then you get back to the same topic or something like that. And so this is semantic chunking. Second technique. And a third technique that's quite powerful as well is to use a language model to do chunking for you. The idea behind this is interesting because you take a language model that's trained to create propositions, these semantically isolated and independent sentences for you. You give it your paragraph or your chunk of data, and it will now generate these propositions. And now from that, it will also kind of accumulate these propositions into sentences and maybe even the sentences into passages so that now you can retrieve based on these kind of glued together propositions. And this is also quite powerful. And then you can decide whether you want to retrieve based on propositions or uh, combinations of proposition sentences or even combinations of sentences called passages. And this comes from a recent paper that we reviewed, and the model is also open source. You can see the link here. If you're interested in following along with these recent developments, we do release Weaviate paper reviews where I cover weekly some of the advancements that are happening in the field, and and they're very digestible 1-2 minute summaries of papers from academia, mainly focused around RAG, information retrieval, that sort of thing. Okay. The other thing that you can also do here is filtering with metadata. This is one of those techniques that is very powerful, and it's very simple actually. The idea is that you can store metadata along with vectors to choose what's relevant and what's not relevant to a particular query. And so the idea here is you've got your database, and so you've got a metadata that tells you the user, so Alice, Bob, John, and then you've got a vector capturing that data. The query comes in, and the query, notice how it's only relevant to one of these users, only to Alice. So what you can do is filter out irrelevant objects, not based on their vector, but based on their metadata, right? The user name here in this case. And you can do this in two ways. You can either pre-filter before you conduct the vector search, or you can conduct the vector search and post-filter afterwards. But this filtering technique is quite powerful, and it further improves the quality of results that come back from the vector database. And the reason why this is part of indexing is because you have to add this metadata when you're indexing the data, so that later on at query time you can actually filter based on that metadata. And so with Weaviate, this is a simple kind of one-liner where you can add one filter, or you can add compositions of multiple filters across multiple metadata fields in directly into your vector database query. If you want to learn more about it, there's a whole kind of explanation page over here at the bottom. Okay, so the next step, two more techniques to do better retrieval, and this has to do particularly with the vector database. The first thing that we're going to talk about is hybrid search. Some other speakers might have talked about this, but the main idea here is that depending on your domain, semantic search, vector search might not be the solution, right? Or it might not be the silver bullet. And so the idea is that in medicine, you've got a lot of abbreviations, right? You've got kind of abbreviations. You've got specific keywords, medication names, disease names, anatomy names, and there, if your machine learning model is not fine tuned on that particular vertical or that particular domain, as was being said earlier, the embedding model might not be able to differentiate between these concepts. Right? And so here, you don't just want vector search. You don't want just some semantic matching, but you also want to be able to match on the keywords that are being mentioned in the medical domain. And the medical domain has an abundance of those. So what hybrid search does is it allows you to conduct both in parallel, and then you fuse the scores afterwards. Right? So in Weaviate, we natively support hybrid search, where if you perform a hybrid search query, it's going to perform both a vector search and a keyword search, and the algorithm underneath that's being used is a BM25 search. And then you get two lists of ranked results for each object. And then you have some sort of kind of rank fusion algorithm that decides how much importance to give to the vector search results versus the keyword search results. And this is quite powerful. In order to go from pure vector search to a hybrid search, all you have to do is change one line of code where you would go from a vector or a near text query to a hybrid query. And now you're kind of accessing this secondary keyword BM25 based search that's being maintained within Weaviate. And so this is quite a powerful tool, and pretty much everybody that uses RAG in production is using some form of hybrid search, um, specifically if they're doing text-based retrieval. Another powerful technique that people are starting to use is query rewriting, and more generally, query transformation. The idea here is to admit that we don't know the best way to talk to language models or to vector databases. So what we do is we get a language model to rewrite our queries to the vector database, as well as our queries or prompts to the language model. And so there's open source frameworks that allow you to do this. For the language model piece here, there's a framework called DSPY that Weaviate integrates with, and there's a link here that you can look at for all the different ways that you can do this. And for the vector database, there's a open source model that also does query rewriting for you. And the idea behind query rewriting is relatively simple. This is the query that the doctor or the patient might identify as important for the vector database. You give that to a language model to rewrite, and this is the rewritten query. Right? And notice how the rewritten query is kind of isolated, chunked. There's smaller sentences that identify the semantics here. And how this works is this particular stack, right? You take the input, which would be this query here. Instead of going directly to the vector database, this goes to a rewriter model that has been trained to do this. And if you want access to this rewriter model, it's over here behind this link. The query is rewritten, so you get the rewritten query, and then that goes to your retriever. And in this case, that's a vector database. It can be a web search as well. And now the documents that come out of the retriever should be a lot more relevant because the query is optimized and rewritten for that particular retriever. And now the LLM that reads reads these documents can now take advantage of those relevant objects. And for DSPY, this is more of an iterative process of automatic prompt engineering where it'll start off with one prompt and then it'll iteratively improve the prompt until you get the best performance. So here you need to specify an input and an output, and then it'll incrementally change the prompt to get you better and better outputs. Okay, and the last thing that I'll talk about is better generation. And so this also has to do with how you can make the things that you're providing to the language model more and more relevant. And so if you actually give it irrelevant things, and it might hallucinate, it might feel the need to use that irrelevant data, which will mislead the generation portion. So the first thing that you can do is this process called autocut. And this is quite simple here as well, right? Even after you've invested all of this time in choosing the right embedding model, choosing the right vector database, using hybrid search, using all these advanced techniques, you might still get back results that are irrelevant. And so what AutoCut proposes is if you can identify that there is a big drop in relevance score, you automatically just cut off those irrelevant scores and you keep this kind of high quality, high relevant objects, and that's all you pass to your generative model. And so the way we identify these irrelevant objects is by looking at jumps in the relevance score. Right? And so how this works in action is the query goes into the vector database. The vector database retrieves your patient cases. So in this case, I'm only retrieving patient cases, no article IDs, just to simplify. And the vector database is also going to output some form of similarity score. Right? And one thing I want you to notice is that the similarity for the top 4 patients is a lot higher than the similarity for the last 2 patients. And the only reason you get the last 2 patients here is because you asked for 6 patients, right? 6, you did a limit of 6 and you got back 6. So what the auto cut feature is going to do is identify that there's a big jump between the first 4 and the last 2. And so we automatically cut the last 2 off, even though you asked for 6, and you'll get back this kind of high quality top 4, and it's going to drop out the last 2 there. And so when you want to actually trigger this with Weaviate, it's a simple kind of parameter in your near text query where you say, I want one list of similar objects. If there is a second jump after that one list, you automatically take that off. If this was a 2, then this would now give me this first continuous piece of similar objects and then the second piece as well. And then the last piece that you can also add to your RAG pipeline, this is also going to improve the relevance of the objects that you're going to give to the language model, is a function called re-ranking. And the idea here is that we've got one model here, usually a bioencoder, that the vector database uses to identify relevance and rank relevance to the query. It pays off to have another much more powerful model look at the query and the objects that are retrieved one at a time and propose whether or not they're actually relevant. And so the idea here is to do another ranking step. That's why it's called a re-ranking step. But now this time using a much more heavier, powerful model that might not be it might not be kind of doable across all of your billions or millions of objects, but it is doable over a smaller subset of candidates that the initial search, the vector database, has deemed worthy. And so in this case, what happens is you go to your vector database, you pass the query in, but now you overfetch. You fetch maybe 15, 20, 25 relevant articles, and you ask the vector database how relevant they actually are. Then you give these relevant patient cases to your re-ranker model, and the job of the re-ranker model is to re-rank. Right? So the re-ranker model looks at the query and each patient case on a case by case basis, one at a time. It performs inference for each one of these, and then it decides, okay, the first patient case here is not actually that similar. It gets a score that gets demoted down to third place here. Right? The third one is actually much more relevant to this particular query, so it gets promoted up the ranks to first place. And it does this re-ranking for each one of these objects one at a time. And now you get this re-ranked score, and now you can take maybe the top 6 or the top 5, and those are guaranteed or most likely to be a lot more relevant because the model is much more powerful and it's trained specifically for this uh, re-ranking phase. And so with Weaviate, to introduce this new pipeline, it's again just another parameter in your near text query where you can configure it to use re-rankers from companies like Cohere, from Gina, re-rankers that are specified on Hugging Face as well. And those are all the techniques that I wanted to cover on a high level overview. You can improve indexing by doing some of these techniques that I've mentioned, retrieval and generation. And a lot of the techniques that I've mentioned here, I, I haven't, by no means have I covered all of the techniques. So if you want a more detailed approach, these are some of the papers that that kind of motivated this talk. There's also a 3-part series from O'Reilly on advanced RAG and uh, building production level RAG. So you can read into these resources. And the last thing that I'll talk about is Verba, which is an open source tool that we've built at Weaviate that gives you a kind of a production level RAG app where you can use it to chat with your own documents. And so initially, if you go to verba.weaviate.io, we've indexed all of our documentation, blog posts, podcasts into it, so you can ask it any question about using Weaviate. But the cool thing is that it's fully open source. You can take Verba and you can put your own documents into it. You can reskin it. So I invite people to have a go at that. And give us a follow if you're interested in this. Love to talk further. And if you have any questions, we can take some of those now. And if you want to connect later on, I'm more than happy to have a one-on-one chat or even just connect online. Thank you so much, folks.
Great. Thank you, Zain. We do actually have a question. Somebody has asked, what language is this in?
Yeah, so Weaviate itself is written in Go. All of the examples that I showed in my slides are using the Python client for Weaviate, though.
How many different SDKs can we use to access Weaviate?
There are so many different. So Python is the most popular one. Then we have a TypeScript and JavaScript SDK. There's also a Go SDK. I believe there's a Ruby SDK as well that was community contributed. So if you go online, there's a whole slew of different SDKs that you can use to access the underlying database.
And what about for Verba?
For Verba, Verba is mainly written in Python. So if you want to modify this, you can have a look at this repo, but this is mainly in Python. So if you have a look at this, you'll see it. There's both the front end and the back end that you can use. And we've also added, so one thing that you'll notice is here, a lot of the techniques that I'm talking about here, they're actually on the roadmap to be added into Verba. So if you look at this, a couple months from now, we'll actually have implemented all of these advanced techniques natively into Verba. So when you start using it, you'll have you can take advantage of those techniques.
Cool. Thank you very much, Zain.